Hello, everybody. Thanks so much for joining our live stream today. I'm Hunter with the SCTE Gateway Chapter Board of Directors, and we're going to be working with Bob Fuller from Belden PPC today. If I haven't mentioned it before, SCTE, the Society of Cable Telecommunications Engineers, is an important part of the cable and broadband industry, and we want you to know that there is room in the SCTE for you if you want to get more involved. If you don't know much about it, check out scte.org, but also don't be afraid to reach out to any of the Gateway Chapter board members, and we'll be happy to share with you as well. Let's get this thing started.
Fiber optics. We're going to talk about some basics at first. Fiber optics is expanding out into the field. Fiber to the home, EPONs, RFOGs, VHubs, there's more exposure to that. But there's a lot of newer people coming into the industry also at different levels. So what we're going to do is a little review of some basics, work our way up to some head-end stuff with muxes, CWDM, DWDM, some troubleshooting issues that we have come along the way, and just try to improve the knowledge and the quality of the fiber optics installs and handlings and questions. If you have any questions, please put them in the chat. If you hear anything or see anything that's good, put it in the chat. I appreciate it. It's kind of different for me doing this without people to get feedback from. Usually this is just it's informal, a lot of back and forth. So please, if you have any questions or if you have any comments, just go ahead and fire them off. So to be started, we locked. There we go. Oh, there we go. All right. Yep. The clicker. Thank you. First thing, as we said, we're starting at the entry level. Some very basics about fiber and working our way up. So the first thing to remember, fiber is going to the home. There's a lot of guys that already do the construction side and splice in the cans, and they're aware of this. There's different types of fiber going to the house. There's raw fiber, there's pre-terminated fiber. Some areas are putting mechanical connectors on them, but anytime you're working with fiber, you have to be careful with how you're handling it and the safety precautions that go with it. So the first thing you have to remember is always wear your safety gear. Glasses are very important. There's a tool called a cleaver that preps fiber to go into connectors or splices. It actually breaks the fiberglass. The fiber glass, and shards can happen. So you have to be careful of those. You don't want them getting in your eye. Don't want them getting in your hands and things like that. So you always have to be careful and wear your protective gear. Shard management is the third item on here, but we're going to talk about that. After you use a cleaver and you have the pieces of fiber left over, it's very important that you put them in a disposable container. A general practice is to do all your work on top of a, did we lose the camera? Okay, the screen went black. I just want to make sure we're good. Okay. Use a disposable container. A general rule has been to do your work on a dark colored mat so you can see the pieces of glass. If they fall, you can pick them up easier. If you don't have that, the practice I used to do was a piece of tape. After I cut them, I would put them onto a piece of tape so they wouldn't blow away and roll away. You have to be careful not to get the fiber ends on your clothes where you can transport them somewhere else, or you would get impacted by it later. Fiberglass, the fibers are organic. So most of the time, if you get it in you, you're not going to really, you're going to feel it because it hurts, but they can't see it because it's clear. And sometimes older glass, it didn't really even cause much of an infection. So it was a real problem if you got fiber in your fingers. If you look it up online, you'll see pictures of x-rays with people with fiber glass shards in their fingers. So it's a real issue. So make sure you use caution and take care of your fiber. Another thing to remember is never look into the end of a fiber. The optic ranges, the fiber optic wavelengths we use are outside of the visible spectrum. You won't see anything. I don't know It's just a habit after you clean things to take a look, but always assume that fiber is active. Some of the total power that we're using as we get into some applications could be enough to cause damage. So always treat fiber like it's alive, never look into the middle of it. There's photosensitive cards that if you show it, it will change color, so indicating that there's light coming out of the end of the fiber. There's also fiber traffic indicators that they can tell you if a fiber is active and which way the light is coming from. If you need to look at that stuff, but just in general, always treat fiber like it's active and never look into the end of it. So parts of a fiber, there's the three main pieces of a fiber, the core, the cladding, and the coating, right? There's other things, strength members and jackets and that kind of stuff, but the fiber optic itself, the core is where the light goes down. The cladding is another piece of glass that has a different refractive index that keeps the light inside the core. The core is only around 10 microns, right? It ranges depending on the fiber and the application, 8 to 12. Multi-mode fiber goes up to 50. But in general, most single mode fibers that you're using, you can say it's around 10. A human hair is about 100, right? So it is much thinner than a human hair. We have to make sure that we keep the fiber clean. One of the biggest enemies of fiber is dirt. So here are some pictures of dirty connectors, some with oil. The last picture is actually from touching it on your finger, the oil that comes off your hands. Always clean the fibers. Very important, especially at installs. The dirtiest fibers you're probably going to see most of the time are brand new out of the bag. There's a lot of habit of just taking out new jumpers, getting a new drop, running it through, and just plugging it in to the house box or into the equipment. Always have to clean fiber, especially when it's out of the bag. Should be scoped. I know sometimes there's equipment differences depending on whether or not you have them. You should always pay attention and clean them. There's different types of cleaners. The most practiced type of cleaner right now is the one-click pen. We have some of the example of those at the end of the presentation today. We'll do a little bit of a hands demonstration about some drops and fiber cleaning and stuff like that. Always protect the end of the fiber. Whenever you're working on it, keep it capped. Don't let it hang out there. Save the protective cap and make sure you take care of the fiber. Another problem with installs and with fiber in general, micro bends and macro bends. A macro bend is a bend that's too tight, but you can see it, right? So if you're in a house box, you're in a node, you're in a rack, and you're routing the fibers. If it takes an angle that's too sharp, that index, the properties between the two fibers doesn't stay, and the light doesn't go down the core the way it's supposed to. It actually goes out the side. If you haven't heard of a tool called the visible fault locator, it puts out a piece of visible light, red light. And when there's a bend that's too tight, you can actually see where it's indicated where you're losing light, where you're getting some impairments coming from. So micro bends, make sure you pay attention to the bend radius. Micro bends are those little impairments that you usually don't see, but still causes problems to the path the light is following. Tie wraps in a splice enclosure, in a head end, if you use tie wraps instead of using Velcro, that's where you can actually distort the fiber just a little, where you can impede the path that it goes. Now, micro bends also happen in splice cases when you have the frozen splice cases. You can have a splice case that's full of multiple muxed nodes and you only lose a few and a few keep working. Each wavelength going down the fiber takes a different path, and a small micro bend can distort that. Like a suck out in RF that distorts some RF signals, but not all of them, the same type of thing. So we have to be very careful of the bending radius and the handling of fiber. Once it's in a house box, once it's in position, a general bending radius of 10 times the diameter, the radius is acceptable. If it's under tension, you're installing it, you're pulling it, you need to have roughly a 20 times bending radius maintained so that you don't disturb the fiber and cause damage to it. There are some multiple types of fiber connectors. The ones that you're going to see most often probably is the SC. That's the big square one that has a keyway to it. The next smaller one is usually in the optics, like in nodes, in the SFPs and things like that. Those are LC connectors. Those are the smaller ones. They're about half the size of an SC. If you work in a head-end environment, some older data centers or other areas, you might find an FC connector. That's a ferruled connector that's actually round and it screws on. That still has a keyway that you have to line up, but then it screws into position. Not as common as the other two. And the newest type that you probably see in most often is HFOC. It's a hardened fiber optic cable designed to go into MSTs or naps on the outside on the fiber taps, if you will. Weather tight to help keep the weather tap sealed and connect fiber to the house. All of these SC is a ferrule type. So the barrel, the ceramic ferrule that's in the bottom of a connector has a different diameter between LC and SC. SC, FC, and HFC have the same ferrule size, so they can use the same fiber cleaner. LC takes a different fiber cleaner. When we get to talking about some newer ones, you're going to find out that there's other connectors, an MPO connector, one fiber connector that has between 8 and 24 fibers inside of it. That takes a different type of pen. Smaller ones, an MDC fiber that's used in muxes, that has a different kind of pen. So always be aware of the type of connector you have, the type of cleaning device that you need for it, and if you can, the right kind of tip for your fiber scopes to make sure they are clean. All right, so that was a lot of talking going on real quick. So far, so good. Any questions? Everybody good? Very good. So the next part of connectors is color. So a green connector actually has a tip that's angled between 8 and 12 degrees is the tip of an APC connector. That's green. Blue is an ultra polished connector. That's where they are flat, but they are polished, but it's a flat tip. One is better for sending reflective properties away, and one was usually used inside data centers, head ends and things like that. Most important thing to remember now that we're getting into the field with more types of connectors is never put a blue to a green. The two tips can't match, right? One is at an angle, so it's not going to line up with the core, and there's a chance that when you put them together, you're actually going to damage the tips, which would cause much bigger issues. So never put a blue to a green. In house boxes, in head ends, test jumper type things, if you're trying to make fibers reach, there are bulkheads. Bulkheads are like F81s in the RF world for putting two types of fiber together. The color of the bulkhead doesn't matter. It's still just a straight through device, right? Meant to intend, like if it's inside a house box, green, one side of the cable is going to be green, so you put the other one, it looks nice. But if you're using a barrel as a test connection, as long as the two connectors are the same, that's what matters. You get a house box that has a green, but you're using blue connectors, that's not the end of the world. As long as the two connectors are green, that's all that matters. Here's an example of the mix and match like we're talking about. As long as two connectors are the same color, it will work.
I got a question for you on that, Bob.
Yes, sir.
I have heard it said in recent years in troubleshooting in data centers that somebody found a problem troubleshooting fiber. Yeah, there was a physical issue. Oh, we tracked it down to a bad bulkhead. Now, based on what the picture shows, which is just a hole through it, and what you're describing, is that really possible?
I've never seen a bad bulkhead. There could be possibilities of spacings in between. The spacings in between are actually really, really close.
Tight tolerances.
Very tight tolerances. But one of the bigger issues that we have goes back to dirt again. When you go to connect two pieces of cable together, two pieces of fiber, you can actually transfer dirt from one to the other, right? And depending on how hard you push, you can cause things. But technically, I've never seen a bad bulkhead. I've seen connectors where dirt from one gets into another.
Yeah.
I've seen light that was bad. We'll talk about that, burning connectors out. But I've never technically seen a bad bulkhead.
It is a bit illogical, isn't it? When you think about the construction of it.
There's nothing on the inside. It's just a barrel.
It's just a hole.
Just
in the
a hole.
middle, right? That's what I was thinking. Thank you.
Right, but it is a manufactured device, so it could be out of spec and you could have but as long as it clicks, you should have the space. I don't know the facts off of my head. There's a lot of numbers that when you start dealing with cable and look up stuff, that's some really big numbers. If you're curious, look up the air pressure when you put two connectors together in a bulkhead.
Interesting.
It's a really, really high number. And so if there's dirt, you can actually damage the connectors from the amount of dirt on the inside.
Gotcha.
That's why it's important to keep things clean.
Gotcha. And then if the gaps or the manufacturing tolerances, I assume these are probably cast. These are probably molded.
Yep.
Plastic cast, die cast of some kind.
Yep.
If for some reason manufacturing defect was there, you might have too big a gap potentially.
Yes.
And if there's enough of a gap, you're like, how could I be losing 3 dB through this bulkhead?
Right.
Must be a bad bulkhead.
Right. But you take it apart, you clean it, you put a new one in,
Yeah.
but it was dirt.
Gotcha. Okay, cool. Thank you.
All right. You're welcome. Thank you. All right. So that's pretty much for fiber basics. Remember, as we're going to the house, keep them clean, wear your protective gear, treat fiber like it's alive, watch out for your bend radiuses. One last comment on the bend radiuses. I've been lucky enough to go out on some visits with the techs that are installing them. There are clips that are designed by the fiber manufacturers to hold their fiber. I know a lot of guys are still using E-clips and Roker style clips and things to hold them in place. Just be careful. Remember the little micro bend we're talking about with the fiber. There was a guy putting in an E-clip. The drill caught, the clip bent to the side while he just straightened it out. Most of the drops have fiber protection and stuff like that, and it might not cause an issue, but it might. That's one of those little bends where you can cause damage. Might not be an issue right now, but down the road, it's one of those install quality things. So pay attention, take your time. Fiber is rugged, but it still needs to be taken care of. Okay. Any last comments or anything before we roll to the next section? Excellent. Thank you. Questions?
Okay. So question from the chat. Is there a difference in bulkheads and attenuators when it comes to inserting two different style fiber jumpers into them? That question was from Dennis Russell from Madison Communications.
Dennis, are you SC to SC? Is that what you're talking about? But are you talking from manufacturers?
Yeah.
Because you can't match an LC with an SC, right? And so the attenuator should be fine.
Okay.
But some attenuators, most attenuators, like you said, with an SC or an LC on the internal of them, most of the time you get SC pads or UPC pads. It's the same thing as putting two wrong connectors together. You got to make sure that if you have an SC connector and you're using optical attenuators, you got to make sure you have an SC pad. The tip of that pad will also match up with the tip of the bulkheads that you're going into. SC pads, UPC pads.
Yeah, and he was saying correct, SC to SC, and that's exactly what he was asking. So thank you. If
Right,
I recall
you.
correctly, your standard optical attenuator in this environment is typically metal with a green or blue sticker to indicate angled versus straight. Is that correct?
Yes, on the end of them. It's kind of hard. You can look in the bulkheads down the end of them and they'll green or blue depending on the manufacturer. That used to be a thing. A lot of them were just the standard black from the old days.
Right.
Black was just a polished connector. Most of the time you read the label. If it says 6-pad, it will have an SC, it will have a APC or a UPC on the side of it.
Or even a green or blue sticker.
Absolutely.
Okay.
To try and keep track. That's the universal color code.
Okay. Yeah, and like you said, you can eyeball it, but then you're right back to that place of, am I eyeballing something I shouldn't be eyeballing?
Absolutely.
Not do that. Too dangerous.
Absolutely.
Good point, though. Thanks
All
for
right.
the question, Dennis.
All right. Thank you. So we're moving on to some fiber theory and some basic information about muxes. Disclaimer, I know this is the SCTE and it's engineering and we're all smart. But sometimes when we start talking about stuff, there's people that like to argue over half a dB. This isn't the forum or the designs where we're doing this. So this is just some general information, some general concepts about how things work, and some issues that we've ran across in the past, and troubleshooting and how things worked. So with that being said, a mux and a splitter. You get into a data center, a head end, a room at an apartment complex. Which one is there? You have one fiber going in common, you have a bunch of ports sitting on there. A splitter takes a common input where the same wavelength goes to everybody that's fed from that area, that splitter. So it's like channel 2 going in, or we'll use wavelengths. Channel 40 goes in, everybody that's in that apartment building gets channel 40. Everybody that's off that splitter gets channel 40. There's higher losses. Everybody gets the same content, the same light, right? Usually when you're using splitters, your light levels can be high, right? I don't know if you guys work with V-hubs or R-fogs. They usually had an EDFA, right? So an EDFA fiber amplifier puts out 16 to 22 dB of light, right? A lot of light. We'll get to those slides in a minute. That amount of light lets it run through a 32-way splitter where everybody has the level that's needed to make their ONUs and equipment work. Right? So splitter, everybody gets the same. A mux is based on wavelengths. So out in the field, the nodes, RFI, regular node splits where we're doing the 4x nodes and things like that, EPON nodes, the node itself, those work on muxes. Every location gets a different wavelength. And so the device that looks like a splitter that has multiple ports coming off of it, each one is actually different content. And all those different wavelengths go back onto one common fiber, right? So a splitter, everybody gets the same. A mux, everybody has different. Light levels are actually going to be a little bit different about levels to be aware of. So please try to pay attention to the type of system you're working on so that you know if it's a splitter or a mux. If you pull the input onto a mux, you can take down 24 nodes. If you pull the splitter, the input on a splitter, you take down 32 apartments, right? In general, that's kind of like how it works. So just be aware of the system that you're working on and the architecture. All right.
I do have a question on that front, and it might be something that you're going to cover down the road. If so, that's fine. Let us know. But in your splitter example, like 32 or 40 apartments, everybody's sharing that same downstream wavelength.
Yes.
What mechanism separates the different customers, since it's not wavelength like we would do in the mux example?
So it's basically like on the RF world where everybody had the same upstream, everybody worked it, and so it was division by time.
Gotcha.
That's the same thing how it
Same
works.
principle, time
Same
division.
principle. Right.
Okay. Gotcha.
Controlled by the modems, controlled by the CMTSs and the management of that kind of stuff. So everybody still gets there, and it's just a different way of delivering the RF to the modem. But it's all common because we just basically moved the node where everybody had the same wavelength, and then they all had the same RF. We'll just move the wavelength closer, and each ONU is basically a node.
I got you. Okay. Thank you.
Okay. All good? With muxes, that's wave division multiplexing, muxes for short. A mux puts wavelengths together, a demux separates them, right? So there's two styles. For the longest, for the most part, Metro E, commercial services, nodes ran off of a coarse wave division multiplexing, CWDM. For the most part in the cable industry, you ran them with 8 channels, right? They were separated by 20 nanometers. So you had 1510, 1530, 1550, right? 1470, 1490. Usually about a DWDM stands for dense wave division multiplexing, where transport actually puts up to 80 wavelengths on one fiber. They're separated by 0.8 nanometers or smaller. That's the major difference between the two, is the amount of channels that you can put into them. Some companies right now are doing a standard of about 48 channel muxes for the RFI nodes. So older designs where we had 4 nodes, 1x4 nodes. Well, now you have a mux in the head end and in the field that's putting 24 nodes together into one fiber. So muxes come in a couple of different flavors. You've probably seen some of these before, where it is a rack mount that has the 2 snap pins on it. That's called an LGX style. There's a newer style for the newer builds that comes in a cassette model with the muxes. They still do the same thing. They still have the same components. It's just a different format for density. There's more fiber being deployed, so head ends and plant need to pay attention to how they're managing their space. So density is a big part. If a mux goes bad, it has to be replaced. Usually lose 2 to 3 dB going through a mux or less. If you have a wavelength that won't pass, you have to replace the mux. There's no serviceable parts inside of it. You can't take it apart, polish a fiber, put it back together. It's all hard spliced. It's all integrated, that there's nothing to do. A mux goes bad, you got to swap it out. The muxes in the plant are in splice cases, are the exact same stuff that's used in head ends, just a different format to fit inside the splice cases. But they are still same basic components that still do the same things. Because of density, this is some of the newer stuff that's going with muxes. There's a new fiber that's called an MDC fiber. It's basically 1/3 the size of a small connector, the LC connector, but it says the same size ferrule. But because it's so small and it's basically 2 connectors put together, they had to come up with a new cleaning pen. So an MDC fiber is one of those unique devices that needs its own cleaning pen. Because they're duplex together, they work in tandem. Some of the connectors are coming with the LC end. MDC goes into the mux, LC goes into the optics, to make the connections. The optics are getting newer connectors on the end, where that little white thing you're seeing is actually a handle to help you release the fibers and insert the fibers. If you ever worked in the head end, sometimes switches get really full. And once you put your hand in front of your face to try and pull a fiber, sometimes you can't see where you're going too easy. So these little handles keep you from making the mistakes and let you see what you're working on. There's been a few mistakes over the years where you put your hand up and everything's really tight. You think you're pulling one, you pull the wrong one. So it's to help try and eliminate some mistakes. All muxes in the newer versions are coming with some common ports. So COM stands for common fiber. AUX, auxiliary, sometimes labeled express, sometimes labeled some other things, is actually expansion. You can take a DWDM mux and you take a CWDM mux, put the CW into the auxiliary port, the expansion port. That DWDM mux is now putting out both sets of channels. So it's a way where you can expand. If you had a 12-channel mux and you wanted to make a 36, you could add another mux and daisy chain them together. That's the world. That's what that port's for. A TP FNR. It's about a 20 dB down test point forward and return. TP FR and O. O stands for optical supervisory. Some places are monitoring their fiber systems. So they're using that as a test point to feed into optical spectrum analyzers, and OTDRs to do constant real-time monitoring. That O is at 1610 nanometers. That's out of band, so you're able to inject and TDR through it. Most ports, most muxes, you can't OTDR through the test points. Just the isolation is too high and it doesn't work. You don't get good traces. We'll talk about that in a little bit. Fiber optics plug into SFPs, nodes, head ends, and now sometimes in people's houses. An SFP is a small format platform, a transmitter and a receiver built into one. We're talking about SFPs because if you don't deal with them and you get an outage one day and you don't have the spare, some places there's not a lot of spares, so they're actually being stored at the office or something. You run into the head end, there's an SFP, you grab it, you run. SFPs come in numerous sizes. Well, they're the same format. 1 gig, 10 gig, 20 gig, 40 gig. There's SFP pluses, long range, short range, extended range. Sometimes they don't work with different manufacturers. They have proprietary things. So the thing with SFPs is to be aware of where your spares are, to be aware of what wavelengths you're using, because some SFPs are tunable, some SFPs are fixed wavelength. So if you're got an SFP in the node that's not transmitting back to the head end and you need a channel 40, you put in a channel 38, it's not going to work. It won't pass through the muxes. So you have to be aware of what you are. If an SFP goes bad, replace it with the same type. It's hard, if not impossible, to get something that's not designed to work inside of it. All right. So it goes for network and for head end. You got to pay attention to what kind of optics you are using. This is a decent topic. Has anybody ever heard of total optical power, optical power addition? So the basic theory is every time you double the number of wavelengths, you add 3 dB to your total power. So if you have 2 SFPs putting out 0 dB and you put them together, if you put that onto your light meter, one fiber, a light meter only reads the total power. You end up with 3 dB reading on your light meter, on your power meter. If you have 4, you went from 2 to 4, there's another doubling. Even though the SFP is putting out 0, you're going to get 6 dB of power on your light meter. So why is this important? So one of the things that have happened in the past with myself, when we're setting up nodes, we're doing node splits. The muxes used to be inside the node housings. And we would set up the links between the head end and the plant techs, and they would call out, they were looking for 0 to 1 dB into their receivers. I got +6. Well, we put a 6 dB pad in the head end. A few years later, tools improve, and we're working on optimizing the head ends, optimizing the nodes, the fields, because you can see the signal to noise, the MERs were below the spec that they wanted. So we went through and we optimized the links. If you went to the individual receivers on the output of the mux, they were reading 6 dB, minus 6 dB, too low. The tech that was out there setting up the node was reading the input of the mux, which was the total power, not the output of the mux. So we removed the 6 pad from the head end. Everybody's light into their receivers went up to 0, and MER improved by 4 to 5 dB. Some areas were up to 10 after we cleaned fibers and everything. So total optical power is an important thing to remember when you're working on fiber. So in the world of muxes, we get to the point where you have a 48 channel mux, 24 channels going to the field, 24 channels coming back from the field. And remember the world of power, right? So if it's a 3 dB SFP and you have 24 channels, so 2, 4, 8, 16, and call it a half. 3, 6, 9, 12, call it a half, 13.5 dB of power, right? Add that to a 3 dB SFP, you now have roughly 16 dB of power. You have the same total power as the output of an EDFA. The first rule of working on an EDFA is unplug the EDFA. You never work on a live EDFA because there's too much power. The pictures on the screen are actually ends of fibers that were burnt. When light levels get too high, you can actually blow chunks out of the end of your connectors. You can burn connectors, you can damage the end of the connectors from optical power. That's why it's real important to pay attention to what's on it. So we had, once again, in the head end, when you're working on the large muxes, we had problems with burnt out fibers because people would preload everything and then go to the patch panel and put it in. And sometimes we try to clean them, you scope them, and they just won't come clean because of the burn and the damage that was done to the end of them. So it's paying attention to what you're working on will make a big difference.
Got a question along those same lines too. I know of at least one company, maybe there's many of them out there, who, for the sake of supply chain and inventory simplification, will only use single mode fiber anywhere, everywhere, always, because then they don't have to order multiple modes of fiber.
Right.
Got your different lengths, but stick to single mode. We only order single mode optics, which is typically minimum 10-kilometer optics, even if you're going 200 feet.
Right.
And I have sort of this sense that those data center environments that burn through a lot of optics on a regular basis, but insist they don't want to switch to multi-mode, and we standardize on single mode and it's fine, and they don't pat it down. So it's 10-kilometer optics 200 feet from each other. Is this the same principle in which you can burn up a receiver or the end of that cable in the same exact kind of way? If you're going through a lot of optics on a regular basis and it's near new normal, your BAU is, well, we just stock tons and tons of 10 gig optics because of this?
Absolutely. That's actually the next slide.
Oh, I'm sorry. Sorry about
Thank
that.
you.
Thank
So
you. It's a real world scenario.
it's a
That's
real
what I was
world
asking.
scenario.
Yeah.
So working the other direction in the RFI environment, we had a new node that was built. And so we got into the habit of leaving fibers disconnected so that, things didn't attach until it was time to. But somebody didn't follow the protocol. Older method they were doing might have been built before we got to this point. But nodes were proofed and balanced and everything was working. But they forgot to get their link losses. So they were sent out to go to each node in the field and shoot back to the head end to document their link losses. Modern OTDRs are designed to shoot hundreds of thousands of kilometers. They can be really powerful, especially when they're tunable. They can shoot through muxes. Most OTDRs can't shoot through a mux. It stops because it's working on a wavelength that doesn't go out all the ports. So the scenario we're talking about is somebody went out with a DWDM tunable OTDR in a urban environment. So the links were less than 7 kilometers each. And they went place to place. 2 days later, we went to activate the nodes, do the cutovers, and 15 nodes wouldn't work. We lost 15 optics because the total power coming back to the head end burnt out all the optics. So with OTDRs, it's important to remember their output level, especially if you're going through muxes and stuff, can be really high. So knowing your test equipment is real important. There are different settings depending on who makes your OTDR, where it's SFP safe mode, right? Or there's what's the other one? SFP safe mode and, hold I lost my clicker. Yeah, it's okay. Just click a button. We should be good. Next slide, and we'll see if it catches up. All right. Did I get a hold of myself? All right. SFP safe mode, or there is another term depending on the manufacturer, where basically what it does is it puts the OTDR into low power so that you don't have a chance to burn out SFPs. There's another, the SFP safe mode actually starts at low power and ramps up until it has a good trace, using the absolute minimum amount of power that it needs to get through the losses and return a good trace to try and keep the optics from getting hit. Most optics have ranges. Where the world is moving over to EPON and RFOG, it's different than the world of HFC. Receivers in the head end used to, receivers in the field used to be set for 0 dB, right? 0 to 1, more or less, right? SFPs in the nodes now are looking for -17. They have a range of a -10 to a -24 or so, depending on the MSO of what you're looking for your range. SFPs, transmitters in HFC used to put out +10. EDFAs to go out to the long range ones were used for single nodes. Well, now an SFP is putting out 3, sometimes 0, sometimes -2, -4, depending on what you're using. So highlight, definitely highlight levels will definitely burn out SFPs and cause receiver damages. There's been a lot of, as we swapped through, there was a lot of outages where the head end was saying, I got light leaving you, but nothing's coming back. And plant is saying, well, I got light leaving to you. And, you know, it's a burnt out optic. Pay attention to light levels. Pay attention to what the design is and what you're working on. So use a power meter, right? Let's see where we are. I've been babbling. I got to take a look and make sure we're still in strain. All right. So power meter, remember total optical power. You know what you're talking about in the world of muxes. That makes an optical spectrum analyzer more important. Those will be in a few slides. Channelized checker. It looks like a power meter, but you can toggle through different wavelengths. Those are better depending on the model you have and how old your stuff is. Some of them were just calculated. They would take the input, and if you had 6 dB of light coming in and you toggled it to 850, it would just do a calculation based on if we were at 1310, now it's at 850, and it would do math and say instead of 0 dB, you got, you know, negative 0.25 or something. Wasn't really accurate, wasn't really there, especially if you had a lot of light coming through it. As long as you're on the output of a mux, you should be good because it's still a single wavelength and those things work all fine. Optical spectrum analyzer is just what it sounds like. It's a spectrum analyzer that shows all the different wavelengths that are on a fiber. In the new environments we're getting into, those are really important to have. OTDRs, troubleshooting, just like in regular fiber. But remember, the bends can impact one wavelength more than others. So the new WDM OTDRs can actually troubleshoot the wavelengths that you're having problems with. So those are important tools. All right. Picture is an OSA. That's one wavelength transmitter and SFP in the head end. Node in the field hasn't been set up yet. You can see this is the node has been activated. We have a return coming back. They're getting ready to turn on the next one. So there's 2 signals leaving the head end, 1 coming back. If you just use a regular power meter, you're going to be off by 3 dB if you're looking at the input of the muxes, right? On muxes, always go on the output of the mux individual wavelength if you can, all right? This is off of test points. Keep the customer working. Don't have to worry about damaging and dirtying fibers as you're troubleshooting. So that's where it's important to use the test points if you can to take a look what's going on. This is an OSA where a mux is getting filled up. If you were to look at the fiber in the wrong place, This is another scenario that's happened with outages in the past. A person at a head end, I don't have light at the SFP, but they go to the patch and they pull the common and they look at it and they, well, I got plenty of light here, but I don't have light at the end. It's got to be a bad mux, or it's got to be a bad fiber jumper, or it's got to be something like that. A lot of wasted time, a lot of problems from just knowing what's the content and what's the architecture that you're working with. If you don't have an OSA and you go troubleshooting at the wrong place, you're going to be chasing ghosts because it's just going to show you light, but it's not going to be telling you the wavelength of the light that you're looking for. OSAs, it's not just graphs. There's a lot of information that come with them, so it's practice, getting used to your test equipment, and it's a new world understanding what optical spectrum signal to noise is, optical signal to noise. So you can actually see individuals where there is a thing called OBI, where you actually get optical interferences. You can see that on individual wavelengths. So if you have one node that's on a common mux that's having issues that other ones aren't, you can actually take a look at it like a spectrum analyzer, looking at one RF channel while you're trying to figure out why the other ones are working. So it's a very real important tool, but also get ready, used to reading the graphs. Sometimes the tools get really clustered when you just look at a graph, right? You can see they're kind of close, but as we're moving, some companies are going with tolerances of how much, like RF used to have adjacent level tolerances. They're looking at RF level to keep the mux balanced out. Looking at the graph, it's hard to tell what it is. Reading the chart, you can actually troubleshoot and see what's going on. So get used to using the tools. Quick breath. Any comments, questions? Everybody good? All right, good. Very important for troubleshooting. First of all, documentation. There's a lot of times where you get to an outage, you get to something going on, an activation or an outage, and there's confusion. So if you get called for an outage, go into the RFI world where you have multiple nodes on a mux. If you just get told to send to one node, or worst case, let's say you have 6 nodes that are out, and you're using your tools and you take a look and it's 6 nodes that are out. Having the right documentation and the right correlation, you can see that all 6 actually belong on a mux, because a lot of the time the muxes are not named the same. The nodes aren't named the same. They're spread out a little bit, within the reach of the fiber. So documentation to troubleshoot where the outages are can help pinpoint to where it's going. Metro E and cell backhaul. Once again, documentations of where the customers are. Commercial customers usually have different service level agreements, and so outages and repair time is important. Instead of taking time to try and find information, if you know where it is ahead of time, it helps you. Same thing, RFOGs, VHubs, different designs. We talked about OBI a little bit. If you don't know where the design is and taking a look at stuff, you don't know if things are built the way that it's supposed to have optimum performance. And fiber docks. You show up at a pole that's down, which fibers are up there? Which ones need to be spliced first if you're doing the outage restorations to try and get transports working and stuff like that. So fiber docks, all of these are important. Takeaway from this slide is the worst time to go looking for information is when you need it. Experience from when I was working in the MSO environment is I would have stuff on my laptop stored with bookmarks because I know where everything is. I haven't used that link in 8 months, and then I go to use it and it's been redirected by IT, or the information is old because they got a new database somewhere. So if you keep up to date, refresh your information of where to find stuff, make sure you stay in the loop of where the stuff is happening. It will help with outage repairs and with troubleshooting. Okay. Some basic tools of troubleshooting. One of the things that's real important that you don't think about is just a good ITU chart. if you're using an optical spectrum analyzer. We talk ITU is like RF channelized. RF, you say channel 58, and everybody says 427.25. You know that. The world of fiber, we're talking terahertz and nanometers and wavelengths. And so you start talking, nobody uses the wavelengths when you get into the DWDM world, they use ITUs. So a good ITU chart. So if you're using an optical spectrum analyzer, it doesn't convert to ITUs, you can look at what you're working on. Easy enough to download off of Google so you can find a chart that makes sense to you and have available if you need it. We had talked about bulkheads. One of the important tools, at least in the head end. You can't OTDR through a mux. So when I was shooting a link to see where things were coming from, I did work up at the SFP level where the final connections were. But most of the time that's up in a rack, and I'm not holding an OTDR while I'm trying to plug it into the fibers that's up there. So a bulkhead with a jumper to reach the test equipment is real important, at least for me, as far as speed and ease of troubleshooting and getting things done. Fiber jumpers, known, good, and trusted fiber jumpers are really important too. I can't say enough about that one. Once again, history. A plant tech goes up in the bucket in a storm, working on outages, checking for where light's going. Where does his light meter and his jumper usually go? Most of the time it goes back in that splicing bucket that's hanging off the side because he's running around troubleshooting things. And then when he's done, the bucket and the tool bag goes back into his bin on his truck. A good, trustworthy optical jumper that is kept clean and kept in good condition where you know where it's going to be in your glove box, you know, in your center console of your truck. Something that's real important so you don't have to worry about what you're looking for. Okay. That's pretty much it. That's some basics of how fiber works and troubleshooting with the newer muxes and splitter worlds. Anybody have any more questions, or is that pretty much what we got for the day?
Questions in the chat.
Yeah.
Okay, that is it for questions in the chat. I want to give them a minute or two, let's say maybe 5 minutes, if it's okay with you, Bob. If they have questions they want to drop in the chat, we'll watch for about 5 minutes. But what we can do in the meanwhile is, if you're good with it, the hands-on portion we were going to do with our folks that are not present today because of the weather, maybe we can take this 5 minutes to set up for that and get a little, change our camera angles and stuff.
Thank you. Yeah, we definitely do that. So it's just some residential drops, some fiber cleaners, and how some mechanical splices are being, connectors are being put on the cable. So if you want to stay and watch that, that's what we'll be coming up with next.
Yep. So give us about 5 minutes, folks. We will, we'll be working furiously in the background. I'll even leave the camera, one of the cameras on, so you can watch us running around like crazy people. And we'll unmute and go through what would have been sort of the hands-on portion, an abbreviated version of the hands-on portion when we get back. Stay tuned. Thanks.
Hi. So we're going to go over a few of the hands-on things that we had brought if there was people in the classroom. Once again, this might be basic for anyone that has been in the industry for a little bit. You might see something new. So please let me know if you have any questions about this. So the first thing we're going to talk about is cleaning pens. So this is an SC cleaning pen. Depending on your brand, they usually have a description of what the pen is for right on the side of it. So an SC, remember that's the bigger square ones that's going to be used most common. A cleaning pen, you flip the top off, and that's for cleaning a ferrule. Designed for a single push. Every time it clicks, that's a rotation of the cloth that's on the inside. Pushing will drag the cloth across the end and clean off the dirt. This brand has a window so you can see how much you have left inside of it. It also has for reaching inside of bulkheads. On the side, this is actually an extender, right? Some people that had never noticed that before. So that actually reaches out so you have some reach to get inside MSTs or naps or bulkheads inside of patch panels. So if you need to extend it, that's usually how it goes. Keep your fiber clean. An LC, as you can see, is a much smaller end of a fiber, right? You definitely can't fit an LC fiber inside an SC cleaner. An MDC fiber is actually two LC connectors really close together. So you can see how the ferrule size is the same, but the diameter wouldn't let you get in without damaging or hitting the other side. Always keep your caps on when you're done so you don't have dirt going down inside the pens. MPO, we really didn't cover this. This is one of the newer things that you're probably going to see inside data center head-end environments, but it's the same thing. It's a fiber tip for a fiber connector that holds multiple fibers in one piece. Still works the same. It's a one-click push. This one here is a newer version of the clay top version where you actually drag a thumb wheel and every time it stops, it cleans. You might have seen those before. They're usually a green or a gray box that has a thumb wheel, exposes tape, and you rotate and pull fibers down. You don't see those as much as you used to. But this style here, you would put an MPO connector on the inside and then rotate the wheel to clean the fiber. All right. So in the outside plant world, the drops that are going to the people's houses, this is an aerial drop. It has a messenger wire. Inside the fiber, it actually has strength members, fiberglass rods that give it rigidity and protect the fiber that's on the inside. This is an HFOC connector. This is actually the fiber cap. So it's designed to be rotated at the bottom base, and then you pull the cap off. As you can see, it's recessed a little bit. Fiber pen should still be able to clean it. Expose it when you're ready to go into the MST connection. If you take a look at the end, I don't know if you can see it. There's like a little arrow shape right there. You need me to rotate it. Can you see it? Okay. So that arrow actually lines up with an arrow at the nap to help you indicate which way to go. You can see the fiber connection actually has a little rounded shape to it so that it's actually keyed to go in to the receiver port. The end of it is actually flared a little bit different also, but that arrow is like a main indicator. One of the things with HFOC fibers to remember is the cap and the cap from the MST are designed to be screwed together. It's a good practice to do that. So if the fiber ever gets removed for any reason, you can replug and keep the MST from getting full of dirt and water. You can see there's a gasket. Same thing, if the fiber gets disconnected, you can recap it and leave it there so it can be reused and still protected. Okay. Some, depending on the drop, the MSO and the manufacturer, this aerial drop actually has a SC UPC connector pre-installed. So you would run the drop and this would go into the house box. Some MSOs are stripping the jacket back so that if they have too much slack, they can store it inside the house boxes. Some are just carrying multiple links. So that's what this one is. There are types of cable where you have the HFOC on one side, and this is just raw fiber. That's the one where you have to put a connector on it. That's where you're going to use a cleaver and other tools to prep it, to put a connector onto it, a mechanical connector. We decided not to do that in a live presentation because remember the fiber shards we talked about, we were trying to maintain them in safety while you're in a classroom environment. So we do have another type of fiber. So this is an underground drop. There's no messenger on it. It still has an HFOC connector on it. But the house box side is semi pre-connected. It's pre-terminated. It has the porcelain, the ceramic ferrule already on the end of it. Right? So this fiber is designed to be used, brought into the location where you want, and then a connector. These parts here are used to put the connectorization part on it to be attached to the bulkheads inside the house boxes. So we brought some of these as an example, if you haven't seen these before, of how this works. So we got to have these samples. On these connectors, if you look at the end, There's a little black dot. Can you see that okay? You need me to rotate it, or can you see it? Okay. This is your alignment key. It's on all these connectors. You'll find a little black dot. Remember where that is, because that's what you're going to need. The first thing you do is you slide a retaining boot on. The next thing would be a mid body. The flanges will go down for the retaining boot to sit onto. If you look, I don't know if you can see them, there's two little circles that indicate the lineup with the circle on the connector. The other way, if you can't see those circles too easily, is there is a notch in this little flange that goes around. There's a notch that you can feel with your fingernail. I don't know. Yep.
It's actually showing up pretty good.
Okay, cool. So you're going to take that circle, line it up with the C side with the key, remove the cap, make sure you save the cap so that you don't lose it. Slide them on and push till you click. You can see the circle inside the window. That's showing up. Make sure you put the cap back on. Always got to protect the end of your fiber. The next is the front body. There's a little keyway that on all SC connectors that shows the orientation of how it goes into the bulkheads, right? Using that side lines up with the circle showing up in the window, and you push that together till it clicks. Should move freely. You push the retaining boot back up, and you have a connected piece of fiber.
Basically.
Yep, without having to do the fiber prep and worry about the shards and stuff. And this is an example of fiber that's used inside a house. Still the same basic. This is an underground drop. It's the same basic fiber that's going inside the houses with the same type of connector. Right. So that's pretty much it. Does anyone have any other questions or anything they would like to hear about?
Chat at the moment.
All right.
This is everything we're looking at is drops and things are all single mode fiber. Is that correct?
Yes, they're all single mode. Most of the time they use single mode fiber. Multi-mode, as we talked a little bit about before inside a data center environment, the core is actually up to 50 millimeters, 50 microns wide, designed for short runs of multiple wavelengths. So we don't use multi-mode usually in any environment other than inside a data center.
And I think you said it in the presentation. They can't hear me, so I'm gonna yell a little bit. I think you said it in the presentation, but what your receive optical levels on either end, wherever the receiver is. What's your ideal range usually? How did you quote it?
It depends. It depends on the optics. If you're in the RFI world, it depends on the company, the optics you're using, and what the design of your company is. So pay attention to what you're working with. But the newer world, the RFI world, the EPON world, most of those actives are looking, most of those SFPs are looking at a -10 to like a -24 kind of window. -17 kind of falls into the middle of that. Actual range of some of these SFPs, once again, go by the different manufacturers, do different things, actually go up to a -5. Over -5, now you're damaging optics, right? So if you have an SFP that's putting out a +4 and it's going real short distance to a node, you're going to have to use some optical attenuation to make sure you don't damage your optics.
So even if it works when we plug it in, well, it works, it's fine. If nothing else, you're prematurely wearing out that receiver.
Absolutely.
And probably on both ends, right?
Absolutely.
So probably both transmit about the same.
Most of the time we set the fiber length is the same.
Right.
And so with the world of SFPs, it used to be the transmitter in the node in the HFC world was a lower powered transmitter than coming back to the head end.
Right.
Because the head end receivers could receive, they were more expensive gear. They could receive a lower light level and still work. Whereas the head end, the field receivers were looking for a 0+1, a higher input to them to have better noise performances. And it was in an environment that they had to maintain. So depending on your optics, but the new world of RFI and EPON, it's lower levels. RFOGs, V-hubs, Those are still like HFC. Those had higher light levels usually
For receive levels.
for
Okay.
receive levels.
Gotcha. Good point. That's a sensitive one for me, so I'm glad we covered that. That's awesome.
Very good.
I'm gonna take exactly what I learned from one of the experts in the field or manufacturers in the field and back to people I know to say, I'm telling you, you're prematurely aging your receivers.
And-
That's why you guys are going through 250 optics a year.
It absolutely is. And that's, once again, I'm not an optical expert, but I've worked in data centers and head ends for, 20 years.
Right.
And we definitely, when the links weren't set up right, we had much more failures than we did when we paid attention to what we were doing.
Makes sense. Okay, very good. Yep, looks like there are no more questions in the chat. I think we've covered off pretty well. Got good hour and 15 minutes of quality content here. Bob, I want to thank you so much for coming. Appreciate
Thank you very
your
much for
time.
having me. I appreciate it.
It's like you and I know, because these folks on the live stream don't have to worry about it. What it took to get us here physically to hang out together today was a bit of an adventure.
It was.
So, but well worth it in my opinion. And as I told you folks on the call, I'm going to get in the picture here with Bob actually. See if I can do this right. See if it works with two of us standing here and it doesn't confuse the poor camera. Thank you guys so much for being here today. We really appreciate you. We hope this is something that's been helpful and useful. If nothing else, hopefully what it's done is spark more questions. If you've got more questions about these specific topics that you want to ask, you can always contact us at SCTE Gateway Chapter. And if worst case scenario, all we do is get Bob on the phone and say, hey, they're asking this. Can you help us figure the answer to this one out? Or, hey, they've asked us 30 great questions. Do you want to come and do a different level presentation? Maybe we do that down the road. That's always a possibility because we get to partner with folks like Belden and PPC and all these outfits that, again, at the end of the day, the mission is to provide the best quality service, to provide the best product, to provide the best solutions. I think I've said it before in some of the other live streams and some of the other presentations and content that we put out on our YouTube channel for SCTE Gateway Chapter. It is very common for multiple providers, manufacturers, and vendors and operators to partner together to say, hey, we got a problem to solve and we're all stumped. If we collectively get together to solve it, it's going to help all of us anyway. That's a very common thing we do. So we all partner well together, take advantage of our partnership to help you, to help grow your career. Again, reach out, make connections. We're happy to see you guys and we hope to catch you next time. Thank you so much. We'll see you soon.
Appreciate it. Thank you very much.